Chemical reactions are governed by strict, inflexible rules. An ignition represents trillions of atomic collisions occurring in a fraction of a second, each one dictated by the laws of stoichiometry. Stoichiometry is the quantitative accounting system used to predict the exact outcomes of these interactions, allowing us to calculate exactly how much reactant is consumed and how much product is formed. Consider the Haber process for synthesizing ammonia. Here, we react 28 grams of nitrogen with 6 grams of hydrogen. Looking at absolute mass suggests hydrogen is the bottleneck because 6 is less than 28. That conclusion is entirely incorrect. Relying on given mass or absolute volume to evaluate a system is a frequent point of failure in JEE exams. Chemical reactions do not respond to grams or liters. They operate exclusively on the physical count of particles and the specific ratios in which they bond. To accurately predict the maximum product a reaction can yield, we must translate all starting data into the universal currency of chemistry, the mole. A mole represents Avogadro's number, 6.022 times 10 to the 23rd particles. This constant allows us to bridge the gap between microscopic atoms and macroscopic measurements. Because molecules have different molar masses, 1 gram of a heavy substance contains significantly fewer particles than 1 gram of a light substance. Mass alone cannot tell us the number of reactive units present. This discrepancy means that raw mass, or gas volume, and particle counts cannot be compared directly to determine which reactant limits the reaction. To perform any valid stoichiometric analysis, every single piece of input data must first be converted into moles. Standardizing all inputs into moles creates the required mathematical baseline for the entire algorithm. Without this conversion, the resulting predictions lack a factual basis. We begin phase 1 of the process, the conversion hub. This hub standardizes different inputs. For mass, we find moles by dividing the given grams by the substance's molar mass. When the problem provides a count of individual particles, we divide that number by Avogadro's constant. For gases at standard temperature and pressure, 1 mole occupies 22.4 liters. We divide the given volume by this standard to find the mole count. In solution-based chemistry, we find the number of moles by multiplying the molar concentration by the volume in liters. A common error involves using volume in milliliters. To get an accurate mole count, you must convert the volume to liters before multiplying by molarity. These 4 formulas serve as the specific pathways required to enter the chemical system's logic. Once disparate inputs are standardized into moles, the reactants can be compared using the mathematical rules of the reaction. Phase 2 involves the ratio matrix, which is derived from a perfectly balanced chemical equation. The coefficients in a balanced equation act as absolute mathematical constraints, defining the exact proportions of reactant consumption and product formation. In the combustion of hydrogen, the balanced equation establishes a fixed 2:1:2 ratio. This ratio dictates that 2 moles of hydrogen must react with exactly 1 mole of oxygen. This proportion holds true for moles, particles, and, for gases at the same temperature and pressure, volumes. If the equation is unbalanced, the ratio matrix is incorrect, and any subsequent calculations will fail to reflect the actual chemical process. The balanced equation provides the structural framework for the reaction. It gives the moles we calculated in phase 1 their functional context. We use that context to identify the limiting reagent. This is the substance that is completely consumed first, setting the limit on how much product can form. We return to the Haber process example. After converting our original masses to moles, we find we have an inventory of 1 mole of nitrogen and 2 moles of hydrogen. Method 1 is ratio analysis. The equation requires 1 mole of nitrogen for every 3 moles of hydrogen. However, our available inventory only provides 2 moles of hydrogen for our nitrogen. Because we lack the 3 moles of hydrogen required by the ratio matrix, hydrogen is our limiting reagent. Nitrogen is present in excess. For complex problems, method 2, product projection, provides an alternative verification. Here, we calculate potential yield of ammonia from each reactant independently. 1 mole of nitrogen could produce 2 moles of ammonia, while 2 moles of hydrogen can only produce 1.33 moles. The reactant projecting the smaller amount is the true limiting reagent. To find the amount of excess reagent remaining, we subtract the amount consumed by the limiting reagent from the initial starting amount. The 6 grams of hydrogen that appeared significant in our initial mass-based comparison was actually the mathematical bottleneck once converted to moles. The limiting reagent alone determines the theoretical yield, the maximum output possible under ideal conditions. Theoretical yield represents a perfect mathematical model. In practice, several real-world constraints reduce the actual amount of product recovered. On the input side, we must account for the purity constraint. Reactants often contain inert materials that do not participate in the reaction. We calculate the pure mass by multiplying the total given mass by the percentage purity. Only this pure mass can be used to calculate the starting moles. On the output side, we apply the percentage yield constraint to account for losses during the process. Side reactions, incomplete conversions, and material loss during purification steps often result in an actual yield that is lower than the stoichiometric prediction. To find the percentage yield, we divide the actual mass recovered in the lab by the theoretical yield calculated from the limiting reagent. Solving advanced numerical problems requires calculating the stoichiometric baseline and then adjusting it for these two constraints. This algorithmic workflow can be summarized into 4 actionable steps. Step 1. Balance the chemical equation to establish the mandatory ratio matrix. Step 2. Determine the pure mass of your reactants and convert all starting quantities into moles. Step 3. Identify the limiting reagent using either ratio analysis or product projection. Step 4. Calculate the theoretical yield based on the limiting reagent and apply any percentage yield constraints. By bypassing the mass fallacy and following this framework, we can accurately determine the quantitative limits and expected outputs of any chemical system.